Section: Introduction. In this section, we explore the background and significance of large language models, LLMs. These models have made impressive strides, showing high fluency and accuracy in tasks like translation and answering questions. Their impact is growing in areas such as healthcare and education. We anticipate that future models will be even better at understanding context, operating efficiently, and adhering to ethical standards. However, we still face critical questions. Can these models genuinely grasp language without real-world experiences? What are the risks of depending on artificial systems for tasks that usually require human judgment? A major concern is the phenomenon of hallucinations, where models produce plausible but incorrect information. Despite improvements, these errors are a persistent challenge, leading us to wonder if we can ever completely eliminate hallucinations or if we must learn to manage this limitation. At the heart of LLMs is a straightforward principle: predicting language patterns. Essentially, the main function of an LLM boils down to asking, given a series of words, which word is likely to follow. Using a transformer-like structure, the model calculates the likelihood of the next word based on the previous ones. As we scale these models, we notice a curious occurrence. They seem to exhibit intelligent behavior. However, it's important to remember that the model doesn't actually think or understand truth. It simply mimics human thought processes very convincingly. When it comes to how LLMs generate language, they operate on tokens, which are the basic units of text. These tokens can be whole words, parts of words, or even single characters. Special tokens are crucial for the model's functioning, such as indicating the beginning and end of a sequence. For example, if we input the sentence, "The cat sat on the mat," the model first converts each token into a numerical form called an embedding. However, these embeddings need positional encoding to understand the order of words. Absolute positional encoding solves this by adding a unique pattern to each token's embedding based on its position, using sine and cosine functions. The process involves creating a semantic embedding, generating a positional encoding vector, and then combining these two to capture both meaning and position. The self-attention mechanism then assesses how much each word relates to others, allowing the model to understand connections, like between the mat and the cat. While absolute positional encoding has its benefits, it struggles with long sequences. Relative positional encoding, on the other hand, focuses on the distance between words rather than fixed positions. We also discuss rotatory positional encoding, ROP, which combines both absolute and relative positional encoding into one vector. This method uses complex number properties to store position through a multiplicative approach, allowing for a more flexible representation of word relationships. Finally, we note that beyond transformers and self-attention, researchers are investigating alternative methods to enhance the efficiency of LLMs, tackling computational challenges and improving overall performance. Section Summary. In this section, we explore the advancements and challenges of large language models, LLMs, highlighting their impressive capabilities in language tasks while questioning their true understanding and the risks of hallucinations. We also discuss the mechanics of LLMs, including token processing, positional encoding, and the self-attention mechanism, emphasizing the evolution from absolute to relative positional encoding to enhance model performance. Section: Linear RNNs. In this section, we discuss linear recurrent neural networks, LRNNs, which merge the sequential processing of traditional RNNs with the speed advantages of convolutions, leading to faster inference. LRNNs not only learn parameters but also their own architecture, and they do not rely on iterative methods like backpropagation. They consist of three main types of weights: those from input to the reservoir, within the reservoir, and from the reservoir to the output. The output neurons can overlap with the input neurons. All these weights are organized into a transition matrix, which we can break down into a Jordan form. We analyze the eigenvalues of this Jordan matrix and remove blocks with the smallest eigenvalues, allowing us to create a smaller network in one step. Next, we introduce Mamba, which represents a significant step forward in sequence modeling, providing an alternative to attention-based models like transformers. Built on state space models, SSMs, Mamba introduces selectivity through data-dependent gating and adaptable matrices, improving performance. It uses a data-dependent step size and matrices that allow for efficient processing of sequential data. Mamba achieves performance similar to transformers while being efficient for long sequences, running much faster by eliminating the quadratic bottleneck found in attention mechanisms. Following Mamba, we have the Jamba hybrid model, which combines transformer and Mamba layers with a mixture of experts module. This model takes advantage of the parallel processing capabilities of transformers and the efficiency of SSMs, using data-dependent matrices and step sizes. Jamba can manage long contexts while requiring less memory than similar models, achieving significantly higher throughput. We then turn to Kolmogorov-Arnold networks, KANs, which are based on the universal representation theorem. KANs approximate complex multivariate functions using simpler single-variable functions. The Kolmogorov-Arnold theorem states that any multivariate function can be represented as a composition of continuous single-variable functions, with addition being the only true multivariate function. Unlike traditional multilayer perceptrons, KANs use learnable activation functions on edges instead of fixed ones on nodes. In the realm of transfer learning, we recognize that despite various architectures, large language models, LLMs, can still produce hallucinations. We can employ techniques that enhance LLM performance without changing their core structures. Pre-trained models are versatile but may not fit every application perfectly. Transfer learning helps align model parameters with specific data, boosting performance. We also explore parameter-efficient fine-tuning, PEFT, which updates fewer parameters than traditional fine-tuning, making it less resource-intensive. This approach can involve new parameters, a selected subset of existing ones, or a combination of both. Key methods include adapters, which add small trainable modules for fine-tuning, and bitfit, which only modifies bias terms and the classification layer, significantly reducing the number of parameters. Low-rank adaptation, LoRa, allows us to indirectly train dense layers by optimizing lower-dimensional matrices, keeping pre-trained weights frozen. This method reduces the number of parameters significantly by factorizing updates into low-rank matrices, demonstrating the efficiency of linear algebra in our approach. Section Summary. In this section, we explore various advanced neural network architectures, including linear RNNs, which enhance inference speed by combining sequential processing with convolutional benefits, and Mamba, which improves sequence modeling efficiency with data-dependent matrices. We also discuss Kolmogorov-Arnold networks that approximate multivariate functions using simpler univariate functions, and highlight transfer learning techniques like parameter-efficient fine-tuning, PEFT, that optimize model performance while minimizing computational costs. Section: Combining PEFT techniques. In this section, we explore how we can combine PEFT techniques to boost efficiency. For instance, we can use adapters alongside LoRa. Next, we discuss retrieval augmented generation, or RAG, which helps bridge knowledge gaps. While fine-tuning enhances the performance of large language models, LLMs, on specific tasks, it doesn't always guarantee that the information they produce is accurate. RAG addresses this by merging the capabilities of language models with information retrieval systems, enabling the model to generate content based on reliable, up-to-date information. To explain RAG simply, we have an output, which we call Y, generated by the language model G, based on the input X and relevant information retrieved from an external knowledge base, denoted as R, X. In the retrieval process, we convert both the input query and the documents in the knowledge base into dense vectors. These vectors, created by encoding functions, represent the meaning of the text in a comparable format. To find the most relevant documents, RAG compares the query vector with the document vectors using similarity measures. For example, cosine similarity checks how closely aligned the directions of two vectors are, while the dot product multiplies the components of the vectors for a straightforward comparison. After calculating similarity scores, we retrieve the top k most relevant documents through two main steps. First, we use approximate nearest neighbor (AN) search methods, like hierarchical navigable small world (HNSW), to quickly find the best matches. Then, we re-rank these top k documents using more detailed methods to ensure we select the most accurate information. In the generation process, we first augment the input by combining the most relevant documents with the original input. This augmented input provides the language model with more context grounded in factual information. The model then generates the final output based on this enhanced input, ensuring that the output is both relevant and accurate. We also address hallucinations in LLMs, which occur when these models produce false or inconsistent content. Hallucinations can happen when the model fills in gaps with plausible sounding but incorrect information, ranging from subtle inaccuracies to completely fictional claims. It's crucial to understand that hallucinations can still occur even with the best training or techniques like RAG. We have identified four main types of hallucinations in LLMs. The first is factual incorrectness, where the model provides wrong information based on existing data without creating new details. For example, it might incorrectly state a patient's blood sugar level. Such inaccuracies can be dangerous in critical areas like healthcare. The second type is misinterpretation, which happens when LLMs misunderstand input or context. This can occur in two ways: corpus misinterpretation, where the model misclassifies intent within its knowledge base, and prompt misinterpretation, where it misreads user input due to ambiguity. The third type is the needle in a haystack problem, where LLMs struggle to retrieve specific, correct information from a vast corpus. This can lead to missed key data points or partial incorrectness, where accurate facts are mixed with errors. By understanding these aspects, we can work towards improving the reliability and accuracy of LLM outputs. Section Summary. In this section, we explore how combining PEFT techniques, like adapters and LoRa, can enhance efficiency, and we discuss retrieval augmented generation, RAG, as a method to improve the factual accuracy of outputs from large language models, LLMs, by integrating real-time information retrieval. We also identify various types of hallucinations in LLMs, including factual inaccuracies and misinterpretations, which can lead to the generation of incorrect or misleading information despite the use of advanced techniques like RAG. Section: Fabrications. In this section, we discuss fabrications, which are completely false statements created by the model that have no basis in its training data. Unlike factual inaccuracies, where the model misrepresents real information, fabrications are entirely invented. For example, the model might create a fake scientific study or a non-existent quote from a historical figure. Fabrications happen when the model generates content without any real retrieval support, indicating that no actual information was retrieved, leading to fictional outputs. Next, we explore strategies to identify and mitigate hallucinations in language models. One effective method is chain of thought, COT, prompting. Researchers found that when we use COT prompting, models can tackle complex reasoning tasks better. This approach encourages the model to make its reasoning process clear, which can help reduce logical errors and nonsensical outputs. However, while COT improves performance, it does not completely eliminate hallucinations, as models can still produce reasoning that is logically sound but factually incorrect. To address this, Wang et al. Introduced the idea of self-consistency. This method involves generating multiple reasoning paths using COT prompting and selecting the most consistent answer. The model creates pairs of reasoning and answers, and then chooses the answer that appears most reliable, based on the idea that correct answers are likely to be reached consistently. We also look at uncertainty quantification techniques to manage the issue of models expressing high confidence even when they are wrong. These techniques vary depending on the model. For instance, in softmax neural networks, the model predicts classes based on a probability distribution, which helps quantify uncertainty. Bayesian neural networks treat model weights as distributions, allowing us to sample multiple models for more reliable predictions. Ensemble neural networks consist of independent models that make separate predictions, and we can quantify uncertainty through various methods, such as Shannon entropy or the gradient of the loss function. However, it's important to note that uncertainty quantification can only help identify potential hallucinations. It does not prevent them. With the increasing use of language models in critical applications, there is a need for explanations of how these models reach their conclusions. Faithfulness is a key parameter that measures how accurately an explanation reflects the model's reasoning. One way to assess faithfulness is through Shapley values, which fairly allocate contributions among features in a prediction. This helps users understand how a prediction was made. In conclusion, we have highlighted various techniques aimed at improving each stage of the language model output generation process to mitigate hallucinations. We examine training improvements through architectural advancements, intent classification enhancements via methods like COT prompting and retrieval augmented generation, RAG, and better information retrieval techniques. Output generation can benefit from self-consistency, while post-generation fact-checking can utilize uncertainty quantification and faithfulness measures to assess the correctness of responses. Despite these efforts, we acknowledge that hallucinations in language models cannot be fully eliminated. At every stage, models remain vulnerable to hallucinations, and no matter how advanced our methods become, the potential for hallucination persists. We will delve deeper into each of these aspects in the following sections. Section Summary. In this section, we explore the phenomenon of fabrications in language models, where entirely false statements are generated without basis in training data, and discuss various strategies to mitigate hallucinations, such as chain-of-thought prompting, self-consistency, uncertainty quantification, and faithful explanation generation. Despite these efforts, we conclude that hallucinations in LLMs are ineliminable, as they can occur at every stage of the output generation process. Section. Structural hallucinations can never be eliminated from large language models. In this section, we discuss how structural hallucinations are an unavoidable aspect of large language models, LLMs. We define structural hallucinations as inherent to the mathematical and logical framework of any LLM. When we generate output from a language model, it involves several complex steps, and at each step, there is always a chance of a structural hallucination occurring, no matter how advanced our models or extensive our training data may be. We recognize that our training data can never be fully complete. We cannot provide 100% prior knowledge because human knowledge is vast and constantly evolving, which means our training data will always be somewhat incomplete or outdated. Even if we had complete data, LLMs cannot guarantee accurate retrieval of information with 100% certainty. There will always be some level of ambiguity and potential for misinterpretation. No amount of prior training can completely prevent a language model from generating factually incorrect statements. Moreover, LLMs cannot predict when they will stop generating output, which leads to the possibility of producing any sequence of tokens. This unpredictability results in the generation of inconsistent, contradictory, or self-referential statements. While we could try to fact-check using a complete database, we cannot eliminate hallucinations with absolute certainty. Language models can create not only incorrect information but also self-contradictory or paradoxical statements, leading to logical structures that lack a basis in reality or their own training data. Although enhancing the complexity and capability of our models may reduce the frequency of these hallucinations, we can never completely eliminate them. Next, we introduce some foundational concepts that we will use in our proofs. We draw on information from previous works for further details. Turing machines, introduced by Alan Turing, were designed to explore the limits of mechanical determination of mathematical truths. They consist of a finite set of instructions, a tape divided into cells for writing, symbols that form the machine's alphabet, a read-write tape head, and a state register to track the machine's state. The machine operates by moving the tape head, reading and writing symbols, and changing states until it reaches an accept or reject state. Turing machines can simulate any algorithm, making them relevant for modeling LLMs, and a universal Turing machine can simulate any other Turing machine. However, we must acknowledge the limitations of what computers can compute. No matter how much effort or resources we invest, a computer cannot solve every problem. The concept of the Turing machine helps us understand these limitations, particularly through the idea of undecidability. For instance, consider the set of strings with an equal number of zeros and ones. We can ask a yes, no question about whether a specific string belongs to this set, and a Turing machine can provide a definitive answer. However, some yes, no questions cannot be answered definitively by an algorithm, making them undecidable. We will refer to three specific undecidable problems throughout our paper. The halting problem, which asks whether a Turing machine will halt on a given input, and the acceptance problem, which asks whether a Turing machine will accept a given input. The undecidability of these problems indicates that an algorithm cannot predict its own behavior regarding acceptance, rejection, or running indefinitely on an input. To demonstrate that a problem is undecidable, we can reduce a known undecidable problem to the one we are examining. We define our problem as A, with a hypothetical decider for a called D_A, and a known undecidable problem as B, with its decider D_B. If we assume A is decidable and construct D_B using D_A, we reach a contradiction because the existence of D_B would imply that B is decidable, which we know is not the case. Thus, we conclude that A is also undecidable, meaning there is no Turing machine that can decide A. This process of reduction shows how solving A would also solve B, reinforcing the undecidability of our problem. Section Summary. In this section, we introduce the concept of structural hallucinations in large language models, LLMs, emphasizing that these inaccuracies are inherent to their design and cannot be completely eliminated due to the limitations of training data and the undecidable nature of their output generation. We also discuss Turing machines and undecidable problems, illustrating how these concepts relate to the unpredictability and potential for errors in LLMs. Section: Hallucination is inevitable, claims and proofs. In this section, we prove our earlier claims about hallucination in language model output generation. We start by acknowledging that training data is inherently incomplete. No dataset can ever be fully comprehensive, meaning an LLM cannot possess 100% prior knowledge. All knowledge for an LLM comes from its training data, so one might think that providing a larger dataset would solve the hallucination issue. However, this is not feasible. We show that while increasing data size can lead to a more complete dataset, it can never achieve total completeness. Thus, a larger training set cannot eliminate structural hallucinations. We assert that no training dataset can contain all true facts. To illustrate this, we assume there exists a dataset that holds complete knowledge. We define our dataset as containing all facts, and we consider the statement that there are true facts beyond those in the dataset. In our first case, if this statement is false, we find a contradiction because the LLM would then generate a false statement, indicating that it has hallucinated. In the second case, if the statement is true, we identify a set of true facts not included in the dataset. Since no fact in the dataset can verify these external truths, the LLM generates a statement that cannot be confirmed, which also constitutes a hallucination. From both cases, we conclude that the LLM produces hallucinations regardless of the truth of the statement. This means that the dataset is either incomplete, with true facts that cannot be verified, or inconsistent, with contradictory statements. We demonstrate that true facts exist beyond any finite training database, meaning that no matter how extensive our dataset is, there will always be true statements it lacks. This incompleteness makes it impossible to eliminate all hallucinations through exhaustive training. Next, we address the challenge of accurate information retrieval, which we liken to finding a needle in a haystack. Even if the training data were complete, LLMs cannot reliably retrieve specific information with 100% accuracy. We explore this problem and conclude that if an LLM is tasked with retrieving a specific piece of information from a complex dataset, it may confuse or mix contexts, leading to inaccuracies. We assert that the needle in a haystack problem is undecidable, drawing on the undecidability of the acceptance problem to support our proof. Section Summary. In this section, we demonstrate that no training dataset can be 100% complete, leading to inherent hallucinations in LLM outputs, as there will always be true facts beyond any finite dataset. Additionally, we prove that even if a fact is present in the training data, LLMs cannot reliably retrieve it due to the needle in a haystack problem, which is undecidable. Section. Issues. Fact set finiteness and the nature of the needle. In this section, we address the challenges related to the concept of finding a specific fact, the needle, within a vast collection of facts, the haystack. We need to consider how extensive this collection is. It could range from an infinite number of facts to just a few. Additionally, the characteristics of the needle are unclear. Its length, color, or any specific attributes are not defined. This ambiguity means that the fact we are trying to retrieve is not well specified. For our proof, we will assume that the dataset is infinite and we will incorporate context and correctness into our Turing machine. We start by linking the acceptance problem to the needle in a haystack problem. We assume that the needle in a haystack problem can be solved, meaning the LLM can determine in advance if it will find the correct needle based on a given prompt and haystack. If this assumption holds, we can create a solution for the acceptance problem. However, since the acceptance problem is known to be unsolvable, our initial assumption must be incorrect. Thus, the needle in a haystack problem cannot be solvable. Next, we define the needle in a haystack problem mathematically. We consider a dataset as a subset of all binary strings. Given a prompt, we identify the correct string. The LLM, represented as a Turing machine, only accepts this correct string. The challenge is to determine a specific language related to this problem. If we could decide this language, we would also be able to solve the acceptance problem, leading to a contradiction. Therefore, we conclude that the needle in a haystack problem is undecidable, meaning the LLM cannot reliably predict whether it will find the needle or not. We then connect this to intent classification, which is also undecidable. LLMs struggle with understanding context, unlike most humans who can infer meaning effectively. This lack of reasoning ability makes LLMs prone to misinterpretations, leading to a non-zero chance of incorrect responses. Thus, we assert that intent classification cannot be fully resolved. To prove this, we reduce the needle in a haystack problem to the intent classification problem. We define a sequence from a user prompt and the possible contexts for that sequence. The goal is to retrieve the correct context from the set of possibilities. If we assume that intent classification is solvable, we could create a solution for the needle in a haystack problem, which we know is not solvable. This contradiction shows that our assumption about intent classification being decidable is false, confirming that it is indeed undecidable. The model faces communication challenges, as it cannot be sure if it has understood the prompt, context, or its knowledge base correctly. Section Summary. In this section, we demonstrate that the needle in a haystack problem is undecidable by reducing it to the acceptance problem, which is known to be undecidable. We further establish that intent classification is also undecidable, as language models struggle with context and ambiguity, leading to an inability to accurately determine user intent. Section. Hallucinations are inevitable during generation. In this section, we discuss the inevitability of hallucinations during the generation of language models. We assert that no amount of prior training can completely prevent a language model from producing false statements. We have established several key points. First, no training dataset is ever fully complete. Second, even when a fact is included in the training data, language models cannot retrieve it with perfect accuracy. And third, they struggle to classify intent accurately as well. Some might suggest that improving training could solve these issues, but we argue that this is not the case. We claim that regardless of the training type, a language model will still generate hallucinations. Enhancements to the dataset, information retrieval, or intent classification will not eliminate hallucinations during the generation phase. This is due to the undecidability of the halting problem, which means the model cannot predict how long its output will be or what it will generate. Consequently, it cannot verify its output beforehand, allowing for the possibility of generating anything, including hallucinations. We explain that the halting problem indicates a computer cannot fully understand itself. For instance, a program designed to determine if other programs halt cannot accurately assess its own halting status. We apply this reasoning to language models, concluding that the halting problem is undecidable for them as well. This means our language model cannot know in advance whether it will finish in an accepting state, a rejecting state, or enter a loop for any given input. While some may argue that the halting problem could be decidable for certain subsets of decision problems, we counter this by showing that a transformer-based language model can simulate a universal Turing machine. If we assume a halting decider exists for language models, we can create a decider for Turing machines using this hypothetical decider. However, since the halting problem is known to be undecidable for Turing machines, this leads to a contradiction, confirming that the halting problem is also undecidable for language models. We further emphasize that language models cannot predict their own outputs. The undecidability of the halting problem means they lack full self-understanding. This results in two levels of uncertainty in their output: the specific token chosen at any moment and the total number of tokens in the output. Additionally, there is a chance of infinite generation since the model may never halt, making the length of the output unpredictable. To illustrate this uncertainty, we consider a scenario involving a predictor algorithm that attempts to forecast the output of a language model. If the output is finite, the predictor returns it; if infinite, it rejects. We then analyze a specific algorithm that creates copies of itself and runs the predictor. The outcomes show that the predictor cannot exist, reinforcing that predicting generation is impossible. Section Summary. In this section, we demonstrate that hallucinations in language models, LLMs, are unavoidable due to the undecidability of the halting problem, meaning LLMs cannot predict their own outputs or the length of their generation. Consequently, even with improved training or datasets, LLMs remain susceptible to generating inaccurate or nonsensical statements. Section. LLMs can generate any sequence of tokens. In this section, we discuss how large language models, LLMs, can generate any sequence of tokens. To predict their output, an LLM must evaluate all possible sequences and select the one with the highest likelihood. However, this includes considering an infinite number of outputs, which is impractical. Therefore, an LLM cannot assess all potential configurations beforehand. As a result, given a prompt, it cannot determine the joint probability of every possible token sequence, making it unable to predict its own generation. We have established that LLMs can produce inconsistent or contradictory statements, including self-referential ones. Since an LLM cannot foresee its output, it cannot verify its accuracy before generating it. We previously examined the idea that LLM generations are inherently unknowable. Now, we focus on self-referential sentences, which highlight logical inconsistencies in any language system. For example, statements like, "I am a liar," lack a fixed truth value and would be classified as hallucinations if produced by an LLM, which we have shown can occur with a non-zero probability. We also noted that there can be infinitely many self-referential statements, as any language model can create various paradoxical sentences that reveal the system's inconsistencies. Examples include, "This statement is both true and false," or, "I am currently hallucinating this exact sentence." Each of these would be considered a hallucination due to their ambiguous truth values. The existence of these infinite hallucinatory statements, along with the undecidability of whether an LLM will halt, reinforces that hallucinations are an unavoidable aspect of LLMs, underscoring the limitations of knowledge-based systems. Next, we address the inadequacy of fact-checking mechanisms. We have shown that an LLM cannot determine in advance if its output will be a hallucination and that it cannot retrieve accurate information with complete certainty. Some might suggest verifying the output against a fact-checking database, but we argue that this will not eliminate hallucinations, as no fact-checking can be exhaustive in a finite number of steps. We assert that even if we try to fact-check every generated statement, we cannot completely eliminate hallucinations in LLMs. If we aim to correct a hallucination to match a fact in a limited number of steps, we will ultimately fail. To illustrate this, we will assume the existence of an ideal LLM that provides perfect responses to any prompt and compare our model's output against this ideal. We define our terms. Let sigma represent the alphabet of Turing machines, and sigma denote all possible strings formed from sigma. We define A as a Turing machine representing the LLM and B as 1 for the ideal LLM. We also introduce F as a Turing machine for fact-checking and modifying outputs. The input prompt is denoted as W, and L, W, represents the output of the LLM for that input. We establish a distance function, D, which measures the number of single-character edits needed to transform one string into another, known as the Levenshtein distance. Section Summary. In this section, we demonstrate that large language models, LLMs, cannot predict their own outputs due to the infinite possibilities of token sequences, leading to the generation of self-referential and hallucinatory statements that lack definitive truth values. We also argue that no amount of fact-checking can completely eliminate hallucinations, as the verification process cannot achieve 100% accuracy in a finite number of steps. Section Proof. In this section, we present a proof by contradiction. We start by assuming that there is a finite series of changes that can transform the output of one algorithm, A, into that of another, B. We then construct a decision algorithm, D, for the acceptance problem. This algorithm runs another function, F, on the input that includes a machine M, B, and X. If the distance between the outputs of M on X and B on X is 0 for any iteration, we accept. Otherwise, we reject. We analyze how D decides the acceptance problem for any Turing machine M and input X. If the distance is 0, it indicates that M accepts X, and D returns accept. If the distance is greater than 0, it suggests that M does not accept X, leading D to return reject. Thus, D accurately decides the acceptance problem. However, since the acceptance problem is known to be undecidable, this creates a contradiction, meaning our initial assumption must be incorrect. Therefore, no fact-checking algorithm can completely modify all hallucinations into accurate responses. Next, we illustrate several assertions about large language models, LLMs. We assert that no training database can be completely comprehensive, and even with complete data, LLMs cannot retrieve information with perfect accuracy. Additionally, LLMs struggle to classify intent accurately, and no prior training can fully eliminate hallucinations. We emphasize that no amount of fact-checking can eradicate hallucinations entirely. To demonstrate these properties, we consider a specific prompt for an LLM. The expected response should ideally start at infinity. If we attempt to respond like a human, we might say, "The cat climbed the tree," and then insert phrases indicating how many words are left. This process can continue indefinitely, as we can keep adding phrases about the remaining word count. A human would start with a random sentence and work backward, while an LLM must begin at the leftmost point, or infinity, leading it to hallucinate since starting from infinity is impossible. We observe that each tested LLM significantly deviates from the expected response. This deviation indicates that the difference between the outputs of A and B is notably greater than 0. We will explain how LLMs encounter issues at every stage of their generation process, resulting in the hallucinations we observe. We reiterate that no training database can be 100% complete, as no dataset can prepare an LLM for tasks that require it to predict its own behavior. The model struggles to know where to start, especially when asked to count backward from infinity. Furthermore, LLMs cannot retrieve facts from their knowledge base with perfect accuracy. They are trained to generate sentences of specific lengths, but in some cases, they misinterpret prompts, leading to inaccuracies in the generated sentences. Thus, the expected precision in word counts is often lost. Section Summary. In this section, we demonstrate that no fact-checking algorithm can completely eliminate hallucinations in language models, LLMs, as they cannot achieve 100% accuracy in data retrieval or intent classification. We illustrate this by showing that LLMs struggle to generate responses that require counting backwards from infinity, leading to inevitable hallucinations. Section: An LLM will be unable to accurately classify intent with 100% probability. In this section, we discuss the limitations of large language models, LLMs, in accurately classifying intent. We highlight that none of the 3 LLMs we examined could correctly interpret prompts, leading to misrepresentation of instructions. For instance, when asked to keep on generating, they failed to follow this direction, indicating a lack of understanding. We also note that no prior training can completely prevent a language model from producing false or misleading statements, often referred to as hallucinations. The LLMs can stop generating text at any point, and without clear starting or stopping points, they have a chance of producing random content. Even if we try to fact-check every statement they generate, we cannot fully eliminate these hallucinations. The fact-checking process itself is flawed, as it suffers from the same limitations of infinite generation and unpredictability. We have verified our claims about the impossibility of completely eliminating structural hallucinations with a single prompt. Furthermore, we extend our arguments beyond Turing machines to Oracle Turing machines, where the halting problem remains undecidable. We explain that if we assume the emptiness problem is solvable on Oracle Turing machines, we can construct a method to decide the halting problem, leading to a contradiction. This reasoning also applies to the acceptance problem, proving that it is undecidable on oracles as well. In summary, we establish that the halting problem, the emptiness problem, and the acceptance problem are all undecidable on oracles, which are more powerful than Turing machines. Our findings emphasize the importance of understanding hallucinations for responsible use of LLMs by both researchers and the general public. We believe in the potential of LLMs and AI, recognizing that while hallucinations can lead to inaccuracies, they also offer creative possibilities. As with previous groundbreaking technologies, AI can significantly contribute to human progress if used responsibly, serving as extensions of human thought rather than replacements. Section Summary. In this section, we highlight that LLMs cannot achieve 100% accuracy in intent classification and are prone to generating hallucinations due to their inherent limitations, which extend to Oracle Turing machines. We emphasize the importance of understanding these structural hallucinations for responsible use of LLMs, acknowledging their creative potential while urging users to apply critical thinking to avoid misinformation. Section: Future Work. In this section, we outline potential future work related to our investigation of structural hallucinations, which we have shown to be unavoidable. We may conduct a systematic study to identify these hallucinations before and after we apply mitigation techniques. Additionally, we could explore other causes of structural hallucinations and develop methods to tailor models for reducing hallucinations in specific tasks. Furthermore, we aim to enhance the use of AI by improving AI literacy, ensuring that generative AI is accessible to everyone, and finding ways to make models safer for children and vulnerable groups. Lastly, we will consider regulations surrounding the use of generative AI.